Hello and welcome back to part 2 of the Commodore 64 assembly language programming video. If you watched the first one, you'll know that this is an extension of the training I provided at the Vintage Computer Festival East 2023. And in the first video, we just wrote a small program just to show some aspects of what assembly language programming is all about. I'm not going to go that deep into that information to save time for what I want to do here. I'm just going to jump into getting things started. For this video, I want to demonstrate the conversion of a popular Commodore 64, we'll call it a trick program. It just makes the Commodore 64 do something neat on the screen. And I want to switch over here to another screen here that shows a sheet that is what we used as instructors at the class. There was two people teaching assembly. I was teaching basic, and I was teaching assembly, and it gave me an idea that let's try to convert some of this to machine language counterparts. Now you can see on the screen here, it's just this is part of the printed material that was offered in the basic class. And let me get here so I can scroll this through. There is one at the top called Fast Math, as you can see here. I'm not going to go over that because this is one area where basic is really easy. It will handle complex math for you. You have to do other stuff in assembly to manage math that's beyond 256 values in a single byte. It's not impossible, it's a little too much for this level of activity. So we're going to do something else. I'm going to show they use the OneLiner idea. This is you can see it here, print. It's just a single print line with the random number generator, and it works on a single line of basic, and it just loops itself, and it creates an interesting pattern. You may have already seen this, but I'm going to go in and type it in right now to show what it looks like, except I'm going to use line number 1, so instead of line number 0 there. So 1 print $, and then in parentheses we have to provide a number that represents the character that's going to be printed on the screen. Except we're not going to put an actual integer here. We're going to put a fractional value. This will work. And then to that fractional value, we're going to add the values. We're going to add the value that comes out of the random number function, which is RND, and then you got to put a number in the parentheses. I think the number you put in here changes the seed value for the randomness. I've put in 0. I can put in 1. I'm just putting in 1 right here. So what this will do so far is it will take the value 205.5 and then add the random function returns a value between 0 and 1. So it's a fractional value. So if the fractional value is on a low side, then it'll actually round the value of 205 to either 205 or 206. I believe those are the two values that it uses. But 205 and 206 have a unique relationship to each other. And you'll see how this works. So eventually it just prints out either the character 205 or 206. So we're going to hit a semicolon here so it prints on the next line. So it prints after the last character that printed, and then a colon here so we can get it to go to line 1 again. Okay, I'll run this. And you may have seen this before, but it's a neat little one-liner trick that if you ever find yourself in front of a Commodore 64, like say back in the 80s when they were sold in the department stores, you got to type this in real quick and run it and walk away, and it will produce this kind of pattern. It's a simple maze generator, but it uses a trick that it's just using a character, and you can see that down below in the expanded multi-line version how it's using a graphic character that looks like a slash and a graphic character that looks like a backslash. You know, a little one-liner trick, and this is how it runs in BASIC. So I thought I'd try doing this in assembly. Now let's see here, I don't think I have my PAL assembler set up, so I'm going to load PAL, 8. And while this is loading at real-time speeds, I'm just going to mention, like in the last video, I do have dogs in the house. I actually have cats in the house too, so you may hear barking or meowing. It's springtime, the dogs like to look outside, and if they see a fly or anything small or big, they will bark at it. So, yeah, if they start barking, I will pause this video. You probably won't notice anything past the pause or any kind of delay past the pause, but I'll kick right on in after they settle down. So PAL is in here, and I'm going to run that to load up PAL in the environment. Okay, so at least this got saved. So I'm going to do a little trick here. I'm going to re-enter this line 1. So there's line 1, and I guess I can get rid of line 10. Actually, let's do it this way. Let's hit new to get the PAL program out of the way. Go back up here, re-enter line 1. Okay, so we're all set. But now I want to create the assembly language version of this program. But because PAL works in the basic environment, I can kind of merge it together. Line 1 has my basic version of the OneLiner, and just like in the last video, I'll set up the PAL assembler lines needed for my assembly language version. So we need to put this sys700, and next line 20 we set our options to print the output to the screen and generate object code that's going to be in memory, and that memory point where it's going to run from. The program counter is going to be starting at C00. Okay, from here, what can we do to make the computer print one or the other character randomly to the screen? Well, first thing is we need a random value. And that's kind of the tough part in assembly. In BASIC, I can just call the random function. It gives me a random value that from 0 to 1, that if I multiply by a number, I can get a range between 0 and that number. But we can't easily do that here in assembly. We have to use some tricks. And here's one of the tricks that I've discovered. Let me see if I can get to the right page here. One of the other books that I like inside, or that's useful for programming on the Commodore 64, is a book called Mapping the C64, or Mapping the Commodore 64 and 64C. This book is also available on archive.org. I'll put the links down below. But this book is basically, it takes every possible memory location in RAM from 0 to 65535, or in this case it'll do it from it'll put decimal values and the hex values 0 to FFFF, and it details what each of those locations in memory is designed for. It's a very good reference when you're trying to find something in the Commodore 64 memory map that you want to perform activity on. So where can we get some randomness out of all this? Well, the SID chip generates noise. It can be made to generate noise value, and you can actually read an instant of that value at any time. So white noise is random noise. So the trick we're going to do here is we want to capture a random sampling of noise that's playing in the background but the volume won't be turned on, so we won't hear it. It'll just be playing in the background, constantly generating random noise. SID chip registers are up high in memory, and they're at around the D40. We're at DC0 here. Let's go up a little bit more. Going through this book, okay, so these, I jumped an awful lot of pages, so D4, okay, keep going back here, D8, okay, there we go, D4, okay, alright, there it is. See here it says read oscillator 3 / random number generator. Well, we can read the oscillator number 3, which we're going to be setting up as white noise, but the person who authored this book indicates that it can also be used as a random number generator for games or whatever. So we're going to do the same thing. Now to adapt that, I'm going to write some code here that lets us work the random number generator, and I'm just going to tell you what we're doing. I'm not going to explain why. Just know that this is one way of doing it. So first of all, I want to set a loop here, because just like the basic version, we're going to keep looping through the code that produces output. So I'm going to set a loop label called start equal to the program counter, which just in this case happens to be C000, because we haven't put anything in since we defined the pointer, the program counter. Next, we need to, now I'm going to put a comment in here just to show you how comments works. So I'm just going to put a single line comment that says set random generator, because we're going to kind of turn this on. Line 60. Now, in order to turn on or to have the noise register generate stuff, we're going to set the noise register or the noise voice to the highest frequency it can produce. That way we get the fastest randomness, if you get what I'm talking about here. We get the most random in the fastest way just by letting it generate noise at the highest frequency. So in order to set the highest frequency, we need to set two locations in noise register 1 and noise register 2 because it's actually a 16-bit value. And all we need to do is just load the accumulator with the immediate value of FF, which is 255, and then we store it into two separate locations. While we have this value in the accumulator, we can store the accumulator to D40E, which is noise register number 1, and we can also store it, because we didn't lose the value in the accumulator, it's still there. We can use it again until we change the value in the accumulator. So we can store it in many places as we need until we need to change it. And the second location is D40F. So that basically stored the highest value in both parts, which basically generates the highest frequency. Now, to turn on the noise register, we need to set a certain bit, and I'm going to go back to this book here and show you how that works. We need to set a bit in D412, which is back here. Okay, D412. See where here it says bit 7, select noise waveform? Well, there's 8 bits here. Okay. So we're going to, and this is for voice 3. We're setting noise already for voice 3. The D40E and D40F are for noise voice number 3. So we're going to set this as a noise waveform. So this particular voice creates noise. And we don't need to worry about the other bits. We're not turning any of the other features on. We're only turning on bit 7. And the way to do that is see, we need to set a bit 7 is, okay, let me show you in binary first. So we can, line 90, we can do LDA. Again, we need a new value for the accumulator, so we can put it somewhere. We can do bit 7, bit 6, bit 5, bit 4, bit 3, bit 2, bit 1, bit 0. That is how we can select a single bit, is by putting a 1 in the appropriate bit position. And this will work. But to follow general conventions, it's also the same as saying in hexadecimal 80. Because when you break this down, 10000000, it's actually 2 halves. There's 4 bits here on the upper half and 4 bits here on the lower half. So what we're doing is we're basically, and when we do a hexadecimal value like FF, that's basically saying the first character represents whatever binary value the first 4 bits are, and then the second character is the last 4 bits. So we know the second character is a 0 because these 4 are 0. This character, the first 4, is equal to an 8 because in binary this is the 1's column, the 2's column, the 4's column, and the 8's column. We have a 1 in the 8's column, so that makes it 8. If I put a 1 here also, we'd actually have a 9 because we have 1 in the 8's column and 1 in the 1's column. Add 8 and 1 together, you get 9. So this is the binary representation, but I'm going to stick with hexadecimal, so we need to load the accumulator with 80 hex. And then we store that into the D4 12. And that basically turns on the noise generator. We never set a volume for voice 3, so we're going to leave it off. Now, when it runs, at this point, noise is being created. That if we actually turned on the volume for voice number 3, we would hear noise coming out of the speaker. And I just realized I put start in a spot I didn't need it right now, line 40. So it won't hurt anything if I left it there. I'll actually want to put the start here because we're setting up the random number generator. We don't need to keep setting up the random number, the noise for random number. So I'll just go 110 here. New label, again we'll call it start equals program counter. And I can go up here and get rid of line 40. Just clear that out. Alright, so there's where our label is now. Hit enter. So now, going back to this information here, actually I'll zoom in on what we're looking at. Going back to this information here, we need to be able to take a random value and with it change 205 to either keep it at 205 or change it to 206. Actually it's what is it? The math's throwing me off here. I think we're going from 204 to 205. Well, actually, let's just do it and see if it works. It's half the fun of this. So going back to, I'll go back to here so we can have something to reference while typing in the program. Okay, so we're going to start this loop that's going to keep putting something out on the screen. First thing I want to do, I can get my random sample. So on line 120, I'm going to load the accumulator with the value that can be found at D4 1B. Just like I told you earlier, this is the one that you can use to draw some randomness out of. So we're going to go ahead and load that. And here is where I'm going to do some Boolean tricks. Boolean tricks are where we can change bits in a value by masking out certain bits. For example, this random number, I'm just going to type something here, binary. Let's do 1 here, 1 0 0 1 1 1 0 1 0. That's an 8-bit. Okay, so let's just say this value represents what I just pulled from D41B. We don't need the first 7 bits. They are pointless to us. We just care what the last bit does. This last bit can randomly be a 1 or a 0 depending on when we read the value. So that's all I need to worry about. If I was able to clear out all this, regardless of what it is, but leave the last one, whether it's a 0 or 1, then I have a number here of 1 or a number of 0. And that would be randomly generated, but then I can add that to that 205. I don't care what the other bits are. If they were in there, they will substantially change the value of what I want from it. I just want a 0 or 1. So I only ever want to see what is in that, what they call the least significant bit. So to do that, let's just say we have the random value in the accumulator. Let's mask out all of them by using the AND Boolean function. And what this means is I'll do 130 and I'll use the AND opcode, and this does an AND on the contents of the accumulator. And I'm going to put this in as binary like I showed you before. I'm going to AND it with 7 zeros and a 1. Now what this means is, if this was matched up, and I want to show you on the next line, let's just say this is our random number that came in. Alright, and actually it's going to give me a syntax error, but that's okay. And I just want to put this up on the screen to show something. And I AND that value with this value. What AND means is it'll compare bit after bit. If the first number's bit and the same bit on the number you're trying to AND it with are a 1, it will result in a 1 in that bit. So the same thing with all of them, but since I'm using 0 0 0 0 0 0 0, that will never cause any of these first 7 bits to maintain a 1. There'll always be a 0 because there isn't a 1 there and a 1 here. However, in this last one, there happens to be a 1 here and a 1 there, so my result would be, and I'm just going to type over this again just for effect, will be a 1. So that would be my final number. Ignore the word error. If this number came in from the noise voice like this, well, there's a 0 and a 1. So it's not a 1 and a 1, so it will return a 0. So no matter what these look like up here, as long as this is a 1 or a 0, I'll get a 1 or a 0 here as my final value that sits in the accumulator. It gives me a value of 0 or 1 that I can add to something else. So back here, make sure that line is in. I'll just type over things as I go. So that means our accumulator is only ever at this point going to have a 0 or a 1 in it. So we're going to add that to the number 205. So line 40, we use the opcode add with carry. And we're going to add the contents of the accumulator to very specific value 205. I'm using decimal here to show that we're going to take the value of 205, not the memory location 205, because I'm using immediate mode addressing. The value of 205 is going to add itself to the contents of the accumulator. So we'll either get a 205 in the accumulator in decimal or a 206, nothing else. And in the last video, I showed you how we can output a character to the screen by using the character out kernel call. So we already have the value we want to print. It's going to be either 205 or 206, and we want to then, it's already in the accumulator, so it's already set up to do a JSR to It was FFD2. That was the kernel call for outputting the character to the screen, as if you were typing it in. So line 160, we're going to, I want to put in that we can exit this cleanly. So just like in the last video, we're going to use the get in call to check to see if a keyboard key has been pressed. So we'll call that right away. That was FFE4. When that runs, we're either going to get, if the keyboard hasn't been pressed, the value is going to be a 0 in the accumulator. In other words, we have a 0 state. And if a key is pressed, we're not going to have a 0 state, but we want to check for that 0 state. So if it's a 0 after that call to get in, we're going to, let's see, branch if equal to 0 to start. That's where our loop was up above. So let me make sure that this looks good here. Okay, once again, from the top, set everything up for PAL assembler. Then we're going to load the largest value in the accumulator, FF, and store it in two places in voice 3 of the SID chip so it can generate the highest frequency of noise. Then we're going to load 80 hexadecimal into the accumulator and store that into D412 to turn on the noise effect, the noise sound. Then we're going to start our loop here, load the accumulator with whatever content happens to be in voice 3 at that instant in time, and it with the value of 1 to restrict it to either 0 or 1, add that value to 205, print it to the screen, wait, check for keys, and if none are pressed, it'll go back to start. Now you see how I have a combination of basic and machine language here, source code. If I run this now like I did in the last video, if I didn't have line 1, it will run and compile. So if I run this, this is the basic version. It's actually running line 1, because when I hit stop, it'll say break in 1. But I'm doing this just for convenience of showing you two different things. In order to compile this, I'm going to go back to my big screen here. In order to compile this, all I got to do is run 10. I want it to run starting at line 10 where the sys700 is. So I hit enter. Oh, a bunch of undefined statements. Why do I have those? Let's run this again. See what I did wrong. I'm going to slow down the output. Okay, it looks like it has to do with setting the 10, 20, 30, set random. Actually, I don't see what I did wrong here. Why is it giving me some problems? Oh, I know why. And this gets me from time to time. This is a hexadecimal value, C000. And if you caught this before now and were yelling at the screen, I guess I didn't hear you, but good for you that you've caught it. So, there. Got to use hexadecimal. If you're using hexadecimal values, you got to notate them as hexadecimal values. So let's do run 10 again. Now it's compiling clean. Alright, so I'll hit run again to show you how fast this runs in BASIC. And I'll stop that. And then to run the machine code, or the machine code version of it, since we started at C000 hex, that's the same as 49152. We do a sys to 49152, and untested, we're going to cross our fingers and this works. And there's the machine language version. See how much faster it is. This could be made even faster if you don't use kernel calls, which do take time and some overhead, but this is a good demonstration of how much faster machine language can be. I'll stop that. So that's it. That is definitely not a one-liner in assembly, but it really doesn't take up a whole lot of space either. But this is a proof of concept to show that it can be done. and in the next video I'll show some additional examples from the classroom code that was taught in the basic language classes, and how we can convert that to a machine language alternative. And there may be better ways of doing this. I just did this to demonstrate certain aspects of assembly language. I repeated the use of kernel calls. I added Boolean logic and some mathematical activity to demonstrate something. And I also poked a little bit into using the SID chip, but not to make noise, not to make actual sound, but to leverage the hardware for something that's able to give us what we need. You saw that the output was rather random. I'm going to hold down the control key to slow this, but there is generally randomness in here. Yes, you'll see certain patterns that repeat themselves, but it's not the same thing over and over again, like it's stuck in a non-random fixed pattern loop. And because I put that check for key press in, I hit any key and it stops. Alright, that's it for this video, and I'll create the next one and put it up as soon as I'm able to.